Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will understand how to design the log and anti-log amplifier using the op-amp. Now using the logarithmic characteristics of the circuit components, it is possible to convert the multiplication into the addition and the division into the subtraction. And similarly, it is possible to convert the powers and the roots into the multiplication and the division respectively. For example, let us say you have a signal A, and if you pass this signal through the logarithmic amplifier followed by the scaling circuit which scales the input by, let's say, some factor B, then the output of this circuit will be equal to B times the log of the signal A. And if we pass this signal through the anti-log amplifier, then we can raise the original signal to the power of this scaling factor. Similarly, let us assume that we are passing the output of the logarithmic amplifier through some division circuit which divides the output of this logarithmic amplifier by a factor of 1 by 2. And then if we pass this signal through the anti-log amplifier, then we can find the square root of the original signal. Now this division circuit can be as simple as the voltage divider circuit, and just by changing the division factor we can find the cube root or the nth root of the original signal. So this type of circuit is very useful in finding the RMS value of the signal. So in this way, these log and anti-log amplifiers are very useful in performing the mathematical operations, or we can say that it is an essential part of the analog computer. So apart from performing these mathematical operations, these log and anti-log amplifiers are very useful for the signal compression. So using this amplifier, we can even reduce or enhance the dynamic range of the signal. Now these log and anti-log amplifiers can be designed by using the diode and the transistors. So first we will design this log and anti-log amplifiers using the diode, and later on we will modify the circuit for the further improvements. So here is the simple circuit of this log amplifier which is designed using the diode and the op-amp. So here this diode is connected in the feedback path between the output and the inverting input terminal. Now here let us assume that IR is the current which is flowing through this resistor R, and ID is the forward current of this diode, and VD is the forward voltage across this diode. Now if we apply the concept of virtual ground, then we can say that this node over here will be also at a ground potential. So now if we apply the KVL in this loop, then we can say that the output voltage Vout will be equal to minus VD. And if we apply the KCL at this node, then we can say that this current IR will be equal to the current which is flowing through this diode. And this current IR will be equal to the input voltage divided by this resistor R. Now here the relationship between the forward current of this diode and the voltage across this diode can be given by this expression. So here this IS is the reverse saturation current and VT is the thermal voltage of this diode, while the VD is the forward voltage across the diode and the eta is the ideality factor. Now generally the ideality factor used to be in the range of 1 and 2, and it depends upon the forward current of this diode. So for the ideal diode, this ideality factor should be equal to 1, but in reality it varies between 1 and 2. Now here this reverse saturation current and the thermal voltage are the temperature dependent parameters. So with temperature, these two parameters will change. In fact, this reverse saturation current will almost get doubled after every 10 degree rise in temperature, while the thermal voltage will change with the temperature by this expression. So here this K is the Boltzmann constant and T is the temperature of the diode, while Q is the charge of electron. So if we put all these values and if we evaluate the value of this thermal voltage at T is equal to 300 degree Kelvin or at room temperature, then the approximate value of this thermal voltage will be equal to around 25.8 millivolt. So at room temperature, if you put the value of this thermal voltage in this expression, then the diode current ID can be given by this expression. Now here this exponential term will be much larger than 1. So approximately we can say that ID is equal to IS times e to the power of 38.6 times this diode voltage VD divided by this ideality factor. And in general, at any temperature, we can write this expression ID as ID is equal to Is times e to the power of Vd divided by eta Vt. Now from this we can say that ID divided by this Is is equal to e to the power of Vd divided by eta Vt. Now suppose if we take the natural log on both sides, then we can say that ln of ID divided by Is is equal to Vd divided by eta Vt. That means Vd will be equal to eta Vt times ln ID divided by Is. Now earlier we have found that this output voltage Vout will be equal to minus Vd, and this current IR will be equal to the current that is flowing through this diode, and that will be equal to this input voltage Vin divided by this resistor R. So if we put all these values, then we can say that the output voltage Vout will be equal to minus eta Vt times ln input voltage Vin divided by this current Is times the value of this resistor R. So this is the expression of the output voltage in case of a log amplifier, and as you can see over here, the output voltage is proportional to the natural log of the input voltage. Now we will talk more about this log amplifier at the later part of the video, but now first of all let us see similarly how we can design the anti-log amplifier. So now here, just by interchanging the position of this diode and the resistor, we can convert the log amplifier into the anti-log amplifier. So now here, let us assume that the current that is flowing through this diode is equal to ID, and the current that is flowing through this resistor is equal to IR, and Vd is the voltage across this diode. Now because of the virtual ground concept, this node will be also at a ground potential. So now if we apply the KVL in this particular loop, then we can say that this input voltage Vin will be equal to the voltage across the diode, and if we apply the KCL at this node, then we can say that this diode current ID will be equal to the current that is flowing through this resistor R, that is equal to minus Vout divided by this resistor R, or simply we can say that the output voltage Vout will be equal to minus R times the current that is flowing through this diode. Now we know that the diode current ID can be approximately given as Is times e to the power of Vd divided by eta Vt, and earlier as we have seen, the output voltage Vout will be equal to minus R times this diode current. So we can say that the output voltage Vout will be equal to minus R times ID, or we can say that that is equal to minus R times Is into e to the power of Vd divided by eta Vt. Now as we have seen, this input voltage Vin will be equal to the voltage across the diode. So we can say that this output voltage Vout will be equal to minus R times Is into e to the power Vin divided by eta Vt. So this is the expression of the output voltage in case of the anti-log amplifier. So here are the two expressions for the log and the anti-log amplifiers, and as you can see over here, the output voltage Vout is also depend on the other factors like the ideality factor eta, the thermal voltage Vt, the reverse saturation current Is. Now like I said before, this reverse saturation current and the thermal voltage are the temperature dependent parameters. So with temperature they will change. Now we will talk more about these two factors at the later part of the video, but before that, first of all let us talk about this ideality factor. Now like I said before, this ideality factor used to be in the range of 1 and 2, and because of this ideality factor, the dynamic range of the circuit used to get reduced. So that is the disadvantage of this diode based log and anti-log amplifier, and that problem can be solved by using the transistor based log and anti-log amplifier. So here is the circuit of a log amplifier which is designed using the transistor and the op-amp. Now here in fact this transistor is used as a diode, and this circuit is also known as the transdiode configuration. So if you observe this circuit here, this base is at a ground potential, and because of the virtual ground, this collector of this transistor will also at a ground potential. So basically this collector base junction is at a ground potential. So only this base emitter junction will be active in this transistor. So effectively this transistor will act as a diode. So now let us write down the different currents which is flowing through this circuit. So here this IR is the current which is flowing through this resistor R, and IC and the IE are the collector and the emitter currents of this transistor. Now approximately we can say that this collector current will be equal to emitter current. And if we apply the KCL at this node, then we can say that this resistor current IR will be equal to this collector current IC, and that will be equal to this input voltage Vin divided by the resistor R. Now here let us assume that the voltage across this base emitter junction is equal to VBE, and if we apply the KVL around this loop, then we can say that this output voltage Vout will be equal to minus VBE. So using this, now let us find out the output voltage for this log amplifier. Now here in the given circuit, as this base emitter junction is acting like a diode, so we can write the relationship between this VBE and the IE in a similar fashion that we have written for the diode. And here, as this collector current is approximately equal to this emitter current, so we can write the relationship as IC is equal to IS times e to the power of VBE divided by this thermal voltage Vt minus 1. Approximately we can write this expression as IS times e to the power of VBE divided by Vt, because this exponential term is much larger than 1. Now from this expression we can easily find the relationship between the output voltage and the input voltage. So if we rearrange this expression, then we can write this expression as VBE that is equal to Vt times ln IC divided by IS. Now earlier we have written that this output voltage Vout will be equal to minus VBE, and this collector current IC will be equal to the current that is flowing through this resistor R, that is equal to Vin divided by this resistor R. So from this we can say that the output voltage Vout will be equal to minus Vt times this natural log of this input voltage Vin divided by R times the saturation current Is. So this is the expression of the output voltage for the log amplifier which is designed using the transistor. And as you can see over here, for the transistor the additivity factor is equal to 1. So there is no dependency on the additivity factor. So using this transistor based log amplifier, we can increase the dynamic range of the circuit. So now similarly, let us find out how we can design the anti-log amplifier using this transistor. So here we have just interchanged the position of the resistor and the transistor. Now using the concept of virtual ground, we can say that this collector is also at a ground potential. But here, to make this base emitter junction positive, this input voltage Vin should be less than 0, or we can say that the input voltage should be negative, because here we are using the NPN transistor. So if you want to apply the positive input voltage, then instead of this NPN transistor, we should use PNP transistor. So now in this PNP transistor, if we apply the positive voltage at this node, then this emitter base junction will become forward biased, and we can use this circuit as a anti-log amplifier. So now let us write down the different currents for the given circuit. So here once again let us assume that IE and the IC are the emitter and the collector current for the given transistor, and here we are assuming that IR is the current which is flowing through this resistor R. Now considering the virtual short, this node will be at a ground potential. So now let us apply the KVL around this loop. So we can say that this input voltage Vin will be equal to the voltage across this emitter and the base junction. Now considering we are using the PNP transistor, instead of writing VBE, we are writing a VEB. And now if we apply the KCL at this node, then we can say that this current IC will be equal to the current IR, that is equal to minus Vout divided by this resistor R, or simply we can say that the output voltage Vout will be equal to minus R times this collector current IC. Now earlier, as we have seen, this collector current can be given by the expression Is times e to the power VEB divided by Vt, and as we have just seen, the output voltage Vout will be equal to minus R times this collector current IC. So we can say that output voltage Vout will be equal to minus R times this Is into e to the power of VEB divided by Vt. Now just we have also seen that this input voltage Vin is equal to VEB. So from this we can say that the output voltage Vout will be equal to minus R times Is into e to the power Vin divided by Vt. So this is the expression of output voltage in case of an anti-log amplifier which is designed using the transistor. So here are the expressions for this log and anti-log amplifiers which are designed using the transistor. So using this transistor, the dependency on the ideality factor has been removed. But still, if you observe these expressions, the output voltage still depends upon the thermal voltage Vt and the reverse saturation current Is. So with temperature, the output voltage Vout will change. So now let us find out how we can modify this circuit so that the dependency on the temperature can be removed. So here is the circuit of a temperature compensated log amplifier. So now let us find out how the circuit works, and using this circuit how we can compensate the effect of temperature on the output voltage. So now in this circuit, instead of a single log amplifier, the two log amplifiers has been used. So in the first log amplifier, the input voltage is given, while in the second log amplifier some reference voltage has been given. And in these two log amplifiers, the matched pair of transistors are used. It means that both transistors have a same thermal voltage and the same reverse saturation currents. So now let us say that the output of this first log amplifier is equal to VA. So we can say that the output voltage VA will be equal to minus Vt times ln Vin divided by R times the reverse saturation current Is. And similarly, now let us say the output voltage of this second log amplifier is equal to VB. So this VB will be equal to minus Vt times this natural log of this reference voltage VR divided by R times this reverse saturation current Is. Now these input voltages VA and VB are given to the differential amplifier. Now by selecting the value of this R1, R2, R3 and R4, we can ensure that the output voltage of this differential amplifier is equal to VB minus VA, or we can say that the output voltage Vout will be equal to Vt times ln Vin divided by R times Is minus Vt times ln Vr divided by R times Is. And if you simplify it, then we can say that VB minus VA will be equal to Vt times ln Vin divided by R times Is multiplied by R times Is divided by this reference voltage VR, or we can say that the VB minus VA will be equal to Vt times ln is input voltage Vin divided by this reference voltage VR. So if you observe this expression of this VB minus VA, it is independent of the reverse saturation current. So by using this reference voltage VR and this differential amplifier circuit block, we can remove the effect of this reverse saturation current. But still this output voltage depends upon this thermal voltage. So using this third block, we can eliminate the effect of this thermal voltage. So now let us write down the expression for the output voltage. So the output voltage Vout can be given as 1 plus R6 divided by R5 times this voltage VB minus VA, and that is equal to Vt times this natural log of Vin divided by this reference voltage VR. Now here this third block is nothing but the non-inverting op-amp, but in this third block this resistor R5 is the temperature dependent resistor. So with temperature, the value of this resistance R5 will change. So now if we select the temperature coefficient of resistance for this R5 in such a way that it can nullify the effect of this Vt, and in a way we can nullify the effect of temperature from this log amplifier circuit. So this is one of the way by which we can design this temperature compensated log amplifier. So in this way we can also design the temperature compensated anti-log amplifier, and if you are interested in knowing that circuit, then do let me know here in this poll. You can also comment me in the comment section below. So this is all about the log and anti-log amplifiers which are designed using the op-amp. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.